At 9:42, the real-time gateway recovered from a short network failure. The incident channel celebrated for roughly 12 seconds. Then hundreds of thousands of browsers and phones noticed the connection was available and reconnected together. Authentication traffic jumped. Session storage slowed. Presence updates flooded the event bus. The gateway that had just recovered ran out of capacity and failed again. Nothing malicious happened. Every client followed its retry code exactly. That was the problem. A reconnect policy that is harmless for one device becomes coordinated traffic when an entire population shares the same failure and the same timer. This is the story of a WebSocket Reconnect storm, why recovery can be more dangerous than failure, and how to design a real-time backend that lets clients return without turning the front door into a stampede. WebSockets feel simple because the API is simple. Open a connection, send messages, and reconnect when it closes. Production turns that tiny loop into a distributed system. A connection may live for hours. It crosses mobile networks, load balancers, and deployments. It carries authentication state, subscriptions, presence, and delivery acknowledgements. When many connections disappear together, they also tend to return together. So the real design problem is not merely how to hold a million sockets. It is how to control the rate at which state is created, restored, and synchronized after disruption. We will trace the failure, separate connection capacity from recovery capacity, and build a design that degrades deliberately instead of collapsing dramatically. The first misleading metric is connection count. One successful reconnect is not one unit of work. The client performs a TLS handshake and HTTP upgrade. The gateway validates a token. A session lease is created or renewed. Topic subscriptions are restored. Presence changes are published. Finally, the client asks for events missed while it was offline. That is at least 6 operations crossing systems with different capacity limits. The gateway may accept 50,000 new sockets per second, while the identity service can validate only 8,000 tokens, or the session store can handle only 5,000 lease rights. The slowest dependency defines safe recovery speed. Counting open sockets while ignoring this fanout is like counting people inside a stadium, while forgetting that everyone entered through 4 ticket scanners. Here is the failure path. A regional network interruption closes many connections within the same minute. Every client schedules a retry after 5 seconds. The edge load balancer receives the first synchronized wave and forwards it to the socket gateways. Each gateway calls identity and writes a session lease before restoring subscriptions. The event bus then receives a presence update for every returning user. Latency rises, so handshakes take longer and occupy gateway memory. Some attempts time out even though the server is still working. Those clients schedule another retry, often using the same backoff formula. A traffic spike becomes a feedback loop. Slower recovery creates more timeouts create more retries, and more retries make recovery slower. Adding gateway instances may move the bottleneck downstream faster. Auto-scaling is useful, but it is not crowd control. The client retry loop is part of the backend architecture, even though it ships in a browser or mobile application. Exponential backoff alone does not solve coordination. If every client waits 5 seconds, then 10, then 20, the waves become farther apart but remain synchronized. Full jitter breaks that alignment by choosing a random delay between 0 and the current backoff ceiling. Each client should also have a bounded attempt budget and a maximum recovery window. When the server is overloaded, it can return a retry after hint or close connections with a reason that maps to a slower policy. The comedy version is a nightclub where everyone politely waits exactly 10 seconds before charging the same door again. The polite delay is not the same thing as an orderly queue. A naive client treats every disconnect as an instruction to reconnect as quickly as possible. The delay is fixed, attempts continue indefinitely, and a successful TCP connection immediately begins expensive restoration. A controlled client behaves differently. It uses exponential backoff with full jitter, stops after a bounded number of attempts, and listens to server guidance. More importantly, connection acceptance is separated from full session restoration. The gateway can admit a client into a limited state, confirm that capacity exists, and then restore subscriptions in batches. If the system is under pressure, the client can receive essential messages while presence, typing indicators, and historical catch-up wait. The goal is not the fastest individual reconnect. The goal is the fastest stable recovery for the whole population. The safer path begins before the connection reaches a gateway. Clients spread arrivals with jitter. A regional edge keeps traffic close to the user and isolates failures. An admission service grants short-lived capacity permits based on gateway headroom and downstream health. Only then does a gateway accept the expensive restoration path. The gateway claims a session lease using a conditional right, so that an old connection and a new connection cannot both own the same session. Subscriptions are restored through a regional broker, and fanout workers deliver messages through bounded queues. Backend services publish events without knowing which machine owns a socket. Every boundary has a limit. Arrival rate, active handshakes, lease rights, subscription restores, and outbound bytes. Limits turn a chaotic recovery into a pipeline the system can measure and control. Capacity planning needs two models. Steady-state capacity asks how many mostly quiet sockets each gateway can hold while maintaining acceptable memory, heartbeat, and fanout cost. Recovery capacity asks how many complete sessions the entire dependency chain can restore per second. These numbers can be wildly different. A fleet may hold 1 million open connections, but restore only 20,000 sessions per second, because identity or lease storage is the bottleneck. That means a full regional recovery requires at least 50 seconds even under perfect conditions. Admission should target the smallest safe rate and leave headroom for normal API traffic. Measure handshake latency, authentication latency, lease conflicts, restored subscriptions per second, outbound queue depth, and reconnect success by attempt number. CPU alone will politely tell you everything is fine, while users wait outside. Presence data becomes dangerous when the design treats it as perfectly current global truth. A safer model uses short session leases. The gateway periodically renews a lease containing connection identity, region, and expiry. If the gateway disappears, the lease expires without requiring a synchronized delete storm. Regional presence services derive an approximate online state and coalesce rapid changes before publishing them. Consumers subscribe only to users they actually care about, not to the entire planet. During recovery, the system can delay non-essential presence publication or mark users as reconnecting. This is a deliberate consistency choice. A green dot does not deserve stronger guarantees than a payment. If presence updates compete with authentication and message delivery, presence should wait. Session ownership remains precise, while the visible status is allowed to be briefly approximate. A queue is not backpressure if producers continue at full speed while the queue grows. It is merely a waiting room with an increasingly alarming fire code. Backpressure must change upstream behavior. The admission layer reduces permits. Gateways reject new restoration work quickly and return retry guidance. Subscription restoration enters bounded queues. Presence changes are coalesced, so 10 rapid updates become one current state. Outbound fanout can prioritize direct messages and critical notifications while dropping typing indicators or delaying read receipts. The degraded mode must be designed before the incident, exposed through metrics, and tested during load experiments. Otherwise, the emergency plan becomes a meeting where everyone discovers the word degraded means something different. Backpressure is complete only when the decision reaches the component capable of producing less work. A disconnect creates ambiguity. The client knows the socket closed locally, but it may not know whether the last message reached the server. The old gateway may still believe the connection is alive. A retry may land in another region. Exactly once delivery is not hiding behind a clever WebSocket option. The practical answer is explicit session versions and idempotency. A conditional lease makes one connection generation authoritative. Client messages carry stable identifiers, so retries do not repeat side effects. Server messages carry sequence or event identifiers, so clients can deduplicate and request a bounded catch-up window. Resume tokens expire and are tied to the relevant session state. The transport can be unreliable, while the application behavior remains predictable. This contract is more useful than pretending the network will always explain exactly what happened. The final engineering step is to test recovery as a separate workload. A steady-state test that gradually opens connections will not reveal a reconnect storm. Start with a realistic connected population, interrupt a region or gateway group, and then restore service. Track the time until 50, 90, and 99% of clients recover. Observe retries per client, admission rejections, token validation latency, lease right saturation, queue depth, and dropped optional updates. Repeat the experiment with slow dependencies, partial regional failure, and a deployment during recovery. Verify that retry guidance changes client behavior and that degraded mode preserves essential delivery. The success condition is not that every client reconnects instantly. It is that recovery progresses monotonically without causing another outage. The graph should look boring because boring recovery is excellent engineering. The durable lesson is simple. Recovery is a controlled traffic problem. Use exponential backoff with full jitter so clients do not move as one crowd. Bound retry attempts and honor server guidance. Measure complete recovery capacity, including authentication, leases, subscriptions, and catch-up work. Admit clients at the rate the slowest dependency can sustain. Separate socket acceptance from full restoration. Use conditional session leases, stable message identifiers, and idempotent handling for ambiguous reconnects. Keep queues bounded, coalesce disposable state, and allow optional features to degrade before essential delivery. Most importantly, test the moment when a disconnected population returns. If you enjoy clear explanations of complex engineering problems and important developments in technology, subscribe. We publish a new visual breakdown every week.